Hey everybody, we're here looking at lesson 7-3 in Status Algebra 2. And we're going to take a little further dive into trigonometric functions and real numbers. And you're going to be using the unit circle here. Still, we've been working on that the last couple lessons. We're going to evaluate our different trig functions, including reciprocal trig functions that we talked about earlier. So the big ideas what you got here is the coordinates on the unit circle, radius 1, unit circle. And then what if we move over and we're doing the same sort of thing, but our radius changes? So you're going to see it's the same thing. We're just going to have a multiplying factor involved there. So reminder what a radian is. So we talked about radian earlier. Remember, you have a circle. So here's our circle. And we've got a radius that's r here on the circle. And if you took that radius, imagine it was string or tape or something so you could bend it, and you went one length of that radius on the circle, the angle that would be formed, this angle right here, that I just highlighted in blue, that I've labeled previously here as theta, that theta is actually how big one radian is. And because the radius would just scale up if the circle size changed, that would give you a specific way to always measure angles. Most of you have always heard of 360 degrees. A little side note on that, if you're trying to research why 360, you go way back in time, they picked 360 because it was divisible by so many nice numbers. 2 goes in there, 3 goes in there, 4 goes in there. 5 goes in there, 6 goes in there, 9 goes in there, 12 or 10 goes in there. It was just convenient. Now, yeah, maybe in some places they like to let you just pick things to do based on the convenience factor. But most places that I know in math, we usually like it based on something that's a little more factual, concrete. So this idea that the radius on a circle, when placed on the circle, you're going to end up with, and this is going to come up again also, is how many of these are there around the circle? Well, just remember, circumference is 2 pi r. Sometimes people like to use pi times diameter, but 2 r's are the diameter. So how many of these r's, if you went around the circle, how many of these r's, these strings, if you will, that I just said, imagine that's one of the radii. There's 2, there's 3. You're going to be a little short, and I'll show you why. Well, because how many of these r's are there? When you go around there, there's 2 pi of them. So there are 2 pi radians around the whole circle. Now, I have that on another slide coming up, but if that is 2 pi around the whole circle, that means it equals 360 degrees. And if you divide both by the 2, that means pi radians. And this is going to be like what we end up using for a conversion factor is 180 degrees. So all of that is very much, in my mind, the way math and science works. Pick something that's very concrete and develop it off from it. So anyway, let's keep going. Here's what I was talking about if we're using a unit circle. So again, this is your radius, or 1 unit. And if you pick that 1 unit and went around there, you're going to again get this 360, because how many r's are there around the circle? There's going to be 2 pi. Well, 2 pi, and you know that pi is approximately 3.14, the common number to use for it. So 6.28 if you double it. There's 6 1/4-ish of these radians around the circle. And again, that's going to break down to 180. If you need a little bit more on that, there's lots of YouTube videos out there that explain this again, and listening to a few other people explain it might help you to get a more concrete understanding. Then we move on with this thing called the unit circle. All the unit circle is, it means we're going to use a radius of 1 so that we have nice little numbers that come up. So 1 unit. And so if you use the unit circle, and we're talking about again, it's a total all the way around of 2 pi radians. That means halfway around, we've got pi radians. And if you cut that in half, we're going to have a half of a radian, or most commonly written as pi over 2. If you come down here to 270 degrees, you've got 3 pi over 2. And then we're going to go, you split each of these in quarters, or like this pi over 2 up to here is cut in half. So half of a pi over 2 is a pi over 4. And halfway between the pi over 2 and this pi over here would be 3 pi over 2. I'm sorry, that's not quite right. 3 pi over 2 isn't in that spot. Halfway between a half a pi and a whole pi would be 3/4 of a pi. And then down here, so another way to do it is sometimes I just count them up. So we have pi over 4, this would be like 2 pi over 4, and 3 pi over 4. 4 pi over 4 is that. 5 pi over 4 would be here, 6 pi over 4, same as 1.5. 7 pi over 4, this halfway mark over here in this quadrant, and then back to 8 pi over 4, which gives you your 2 pi. Now, next thing I want to do is, what if we, what are all of these? These are like a third, you know, in between here. Well, if you, I'm going to take those colors off. Let's focus on, well, let's do these. So if we do all of them, and then we'll have to simplify when we're done. So if you look there, we've got, if you split them up into pies pieces, how many pieces of a pie do you have in this top half? Remember that how far many radians around here? Pi. Well, how many parts did I cut it up into? 1, 2, 3, 4, 5, 6. So each one of those are a sixth of that pi. So written commonly as pi over 6, 2 pi over 6. I'm going to count these up again. 3 pi over 6, which is going to again simplify to my pi over 2 or half a pi. Where was I? 3 pi over 6, 4 pi over 6, 5 pi over 6, and 6 pi over 6, which again is going to simplify back to my pi. So the only thing we have to do in there then is, because, and we could keep going. So if we keep going here, we're going to have 7 pi over 6, 8 pi over 6, 9 pi over 6, 10, whoops, 9 pi over 6, sorry. I skipped one. 9 pi over 6 is right down here, which simplifies to my 3 pi over 2. 10 pi over 6, 11 pi over 6, and 12 pi over 6 all the way around to here, which again reduces to my 2 pi. So we've got some of them that we need to simplify or reduce down. They happen to be always right up here on each side of the y-axis. And each of those are going to be thirds. So we got a pi over 3 here. We're going to have a 2 pi over 3 here. If you focused on, let me use a highlighter here, which ones I'm talking about. This, if this is going to really be a mess by the time we're done, but if you're watching it as I go, there's a pi over 3, there's 2 pi over 3. This would be 3 pi over 3 as we go. We're going all the way around here. And then down here, we're going to have our 4 pi over 3, our 5 pi over 3, and we get all the way back, that 6 pi over 3, which is again going to be 2 pi. So let me write those in as we go again. These are just simplifying them out as we went outside. Out here was 3 pi over 3, 4 pi over 3, 5 pi over 3, and all the way around to 6 pi over 3, which is again the same as my 2 pi. But hopefully you see how all those radians go around the unit circle, because they're going to have us use it here on this next one. So if we go over here to our 2 pi over 3, which I just showed you that was going to be right up here. This is a 30, 60, 90 triangles. All the triangles on here are either 45 if we're in the middle of each quadrant, 45, 45, 90. Or all the rest of them, if it's laying down here, it's a 30, 60, 90 with the 30 down here. And if it's up here, it's a 30, 60, 90 with the 30 at the top. So all the way around, that's all you have is the two possibilities, 30, 60, 90 or 45, 45. So on this one, we've got a 60 down here, a 30 up here, 90 here. As we developed, remember with our 30, 60, 90, we talked about on those before, if this is 1, this has to be half of it. And with the Pythagorean theorem, 1/2 squared plus what? I'll call this the y side because I've got it on the vertical, equals the 1 squared. And this 1/2 squared, 1/2 times 1/2 is 1/4. Subtract the 1/4 the other side, we've got a 3/4. So y squared is 3/4. Square root both sides to solve for y. And you're going to have the square root of 3 over the square root of 4, but the square root of 4 is just 2. So for the coordinates right up here, the coordinates there at that point, it's 2 pi over 3 radians. This is a -1/2 right here. And then we just solved for this side right here on the y and got square root of 3 over 2. Now, if you're doing sine, so the sine is opposite, remember, so opposite over hypotenuse. So the opposite side here is the square root of 3 over 2. Over the hypotenuse, remember, we're talking about the unit circle. Unit circle, radius always 1. This is a radius. So sine is really just always going to be the y side because the hypotenuse, we said we're calling always on the unit circle to simplify this. So it's always over 1. So sine of that angle, the 2 pi over 3. I think I told you a long time ago that I oftentimes leave that angle out of here. I'll put it in at the end to make sure somebody doesn't take off points for me on a test. All right, so there's my sine. It's always the y side. Well, if the sine is the y side and cosine is the adjacent, this adjacent side is the x side to the angle here, 60 degrees or 2 pi over 3 radians. The adjacent side is just this -1/2. So if you're understanding cosine is x, sine is y, you wouldn't even have to work this problem. You could just say, okay, cosine of my 2 pi over 3 radians is the -1/2. So for the problem, sine and cosine of that angle, we've got the -1/2 for the cosine, the x. So again, this is going to be something that becomes real key to remember for all of these trig problems. Let's take a look at the next one. So if at a -45 degree, remember -45 degree just means you're going this way. So if it's a -45 degree, this is a 45. Oops, let's draw that a little better. This is a, just pulling this triangle out so I have more room to write on it. It's 45 degrees. So this is a 45, this is a 45, and there's my 90. Remember the radius was 1. So if the radius is 1, if I call this x and this x, we've got x squared plus x squared, 2 legs squared and added together equals the hypotenuse squared. So 2x squareds equals 1. 1 squared is 1, divided by your 2 on both sides. And you've got your x squared to be a half, but we want to know what each of the x sides are. So if you square root both sides right there, let's solve for x. Square root of 1 on top is 1. Square root of the 2 on the bottom. Remember, many places they do not like that to have radicals in the denominator. So we would what they call rationalize the denominator. Square root of 2 times the square root of 2 on the bottom of the denominator here is square root of 4, which is 2. So these two sides here, we've got a square root of 2 over 2. The denominator is not under a square root there. And then remember on this side, over here on my y, I've got a negative because this is the y. So this is the cosine. Remember, we just did the last problem. X was always going to be our cosine. This y, negative square root of 2 over 2, is going to be my sine. So what are the answers? Final answers here. Sine of the negative 45 degrees. By the way, what is that in radians? The negative 45 degree right here? Or these were pi over 4s, so we went pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, which was pi, 5 pi over 4, 6 pi over 4. That at 45 would be 7 pi over 4 if we were doing positive. Or if we're doing the negative rotation, it would be a negative pi over 4 radians. So just a little review there. But anyway, the sine of this, or the sine of this, or the sine of this, because they all are coterminal, they end at that spot on the unit circle, are all the negative square root of 2 over 2. This is the answer for all those. Also, then the cosine at that spot, the cosine at my negative 45 degrees is the x side right here, which was the positive square root of 2 over 2. And we could have had all these same angles for that too. By the way, on a positive cotangent in degrees, that would be 315, right? Because 315 and 45 add up to my 360. So that's just a little extra bonus learning there. All right, what about the Pythagorean identity? Now, they kind of throw this in on the next problem, so I kind of wanted to talk about it. If we call this the unit circle, and we put any triangle in here, remember moments ago when we said since the radius is 1 on there, on the hypotenuse of that triangle, we could put it anywhere we wanted in here, in any quadrant. Radius would always be 1, no matter where you're at. And then you've got your x side and your y side. So isn't it true for a right triangle, x squared plus y squared, sum of the square of the legs equals the square of the hypotenuse? But if you were just listening on the last problem, we always said on these, since so is sine equals opposite over hypotenuse, and I think I just froze my screen. We're gonna have to pause this. And I'll come back to recording. I think I was going too fast, froze it up just a moment. I hope I come back right where we were. And I think we're still recording. So let me see if I can do this just from writing with the mouse over here. So my sine was going to be the y, and my cosine is going to be the x adjacent over hypotenuse 1. And sine, so because x is cosine, we can write cosine squared plus y was my sine, sine squared in place of that y, that's a squared there, equals 1. And that's going to always be known as the Pythagorean identity in these problems. I think I'm going to have to stop this recording. I'll come back and we'll do part 2 and continue with the next problem. All right, I think I've got this back where we were. And so we've got that sine squared plus cosine squared equals 1, or cosine squared plus sine squared. It does seem like more often you see this written the other way around. Doesn't really matter. It's just like these are your y's, these are your x's. So no big difference there. But that's called the Pythagorean identity. And that comes into play with many problems when you get into some more advanced trig. All right, so using that, they say on this next problem, I'm not sure where they thought you were going to just, like, that was just going to fall out of the sky into your brain. But it's based off from what I just showed you on that last slide. So we've got a negative 3 over 5 for the cosine. So this side here, we're still on the unit circle, is a negative 3 Switch to a color that shows up there. -3, we just showed you that cosine is the x. So this is my x side, and my y is 1. So if we're trying to find sine, so they labeled it this way down here, if you were to, we're just going to do Pythagorean theorem. So what are we going to do there? My -3/5 squared plus my y side squared equals the hypotenuse squared. So -3/5 times -3/5. Remember, you just multiply straight across. That's going to be a positive 9/25. So 9/25 plus the y squared equals 1. That little mark out of there. Subtract that to the other side. And this 1 is, remember, that's like 25/25 minus the 9/25 I'm subtracting over there. That means y squared is going to be 25 minus 9. I'm getting like 16/25. And then we want a plain y, not y squared. So we're going to square root both sides. Square root is 16 on top, 4. Square root of 25. We've got a 4/5. I mean, you know, the sign then is the 4/5, but since it's down, and remember this is a third quadrant, letter C from the top, the order that the quadrants go. So this y value right here, the y side, because it's down in the third quadrant, that's got to be a negative. So what is the measure of what are we supposed to be finding here? What's the sign? Sign, which is y. That y side right there would be a -4/5. All right, let's keep going here. We have a problem to practice on there. What about tangent? So 5π/6, remember π/6, that's like 1π/6, 2π/6. This is negative, so I'm going in the negative rotation. 1, 2, 3, 4. -5π/6 would be right there. 30, 60, 90. So this is by -√3/2 on that side. We've developed that before in -1/2, or our unit circle. We did this before, so I'm not going to redevelop, but you can go back and look at that again. We've got a 30, 60, 90, and we're using the unit circle. So the hypotenuse 1, this is half of it, and this side, well, whatever, negative or positive, depending on your quadrant. And the long leg is the √3/2 side. Now, if you need it, you can ask me, or look up another YouTube video that explains 30, 60, 90 triangle unit circle. And you can find many places with different people explaining that. So what's the tangent? Remember tangent, TOA. So the opposite side, the -1/2. So tangent equals opposite over adjacent. Sometimes you're going to know this as opposite's always going to be the y side, over adjacent side's always the x side. So it's the y over the x. So if you went over here to these, the y side -1/2 over the x -3/2. It's going to be positive, divided by negative, divided by negative. I'll just remind you that a 1/2 and the fractions of dividing problem, this was a -√3/2. Divided by the -√3/2. I know one math teacher that used to always explain this as just shorthand is, instead of doing this division where you're going to take 1/2 times the reciprocal, remember that means flip these over. Since it was a negative divided by a negative, they're both going to be positive when we're done. Negative divided by negative is the same as a positive overall. So 2 over the √3. And this person, for a shortcut up here, he would just say, just flip flop and bring it to the top. So you put the 2 over the √3 here. You've got a multiplying by 2 up here and a dividing by 2 down here, or 2 divided by 2 is 1. So our final answer for this is going to be the 1 over the √3. Again, rationalize the denominator. They don't like those square roots left in the denominator. So we multiply the √3 by another √3, and we end up with a √3 over 3 for this tangent. All right, continuing on. Oh, one more example here on the same type of problem. 3 pi, remember, all the way around is 2 pi, right? And we got to go one more pi, so that would be a half of a pi. So that means we're going to be coterminal here with just a pi. Tangent, tangent. Remember we said opposite over adjacent, and on the last example I said, okay, so that's going to be y over x, because opposite usually, opposite is the y side over this x side. So this coordinate right here on the unit circle is -1, 0, right? So what's the y side? 0 over the x, -1. What's 0 over anything? 0. If you would have had the 0 in the denominator, you would have said this was undefined or not possible because you can't divide by 0. But this one is not that case. So, but if you do get a 0 in the denominator, don't forget that's undefined. All right, let's go on to example 4. Keep moving here. So remember, secant goes with cosine. Cosecant goes with sine. And cotangent goes with tangent. So cosine we said was x, so secant's going to be 1 over x. Sine we said was y, so cosecant's going to be 1 over y. And we just did tangent and said that was y over x. So cotangent is going to be x over y. Remember, these are all the reciprocal, those three. Secant, cosecant, and cotangent are the reciprocals. Flip over the fraction. So which one are they're asking for all three, and they're talking about using these. So if I'm doing secant, I'm talking about 1 over x. So my secant, did they label this angle with 135? So the secant of 135 is going to be 1 over, what's the x value over here? -√2 over 2. So 1 divided by it, you're going to be 1 times the reciprocal, or like I said on the last problem, flip-flop, bring it to the top. So you're going to be 2 over the square root of 2. Negative, 1 times the negative is still negative. 2 over the square root of 2. So we're going to rationalize the denominator again. And this is going to end up being -2 square root of 2 over 2. And then those 2's are going to divide out. So our final answer is a -square root of 2. Whew. All right, let's keep going. So we've got the cosecant, abbreviated CSC, of that 135-degree angle. And when we do that one, we're already labeled here on our unit circle. So the cosecant, 1 over the y value there, 1 over your y of square root of 2 over 2. Flip-flop, bring it to the top, dividing by it, multiplied by the reciprocal. However you're going to do that, we've explained that multiple times. 1 times 2 over the square root of 2. 1 over 2 over the square root of 2 we just had right here, rationalizing the denominator again. And we're just going to get a positive square root of 2 that time. So then we move on to the tangent. Hold on, the cotangent. So the cotangent of your 135 over here, you've got your cotangent. It can be the x over the y, and the x over y in this case where we had the coordinates. They're both the same, square root of 2 over 2. It was just that the x value was negative. So we got something divided by itself, so just a -1. All right, hopefully you're getting a little more comfortable with these. Seeing it the first time, I wouldn't necessarily expect that. All right, we have an application problem. We got a radius 4 miles out. I'm looking at the picture, kind of summarizing over here in the paragraph. 30 degrees east of south. So right here, here's my south. 30 degrees east of that would be right here. If you're using your reference triangle here now, here's your 60. Here's your 30. And you've got your right angle right there. 1/2 on this side, over on this side. And then because it's a 4, you're actually going to be multiplying. So the 4 being your radius this time, and this being a 1/2 of that, you're going to be taking a 2 times your square root of 3 over 2 on this side, which is going to cancel, leaving you just a square root of 3. So when they ask what's the final position, we've got the coordinates right here. We've got a 2 on our x, and we've got a square root of 3 over 2 negative down there on the y. So if you were going to try to get to this point, you'd go 2 east and square root of 3 over 2, and most likely you would multiply that out to get an approximate type of an answer for that. And then the square root of 3 over 2. Oh, remember this 2 canceled on that, so that we had 4 up here with that leaving a 2. So a negative 2 square root of 3 is really what ends up in this spot. As this 2 was half, so this we had to double the 4, 1, 2 square root of 3. So the 4 square root of 3. This was a 4 square root of 3 divided by the 2. And I believe that's where we wrap it up. So we've got our trig functions here, x and y, to find the coordinates on the unit circle, 1 the radius, x the cosine, y the sine. And we went a little further than that when we did our other reciprocal functions. Got those all summarized down here. And over here, if we're on, that's the unit circle. If we have a different radius, we're going to end up with that radius being multiplied and divided to get those. So that is a lot in that one lesson. So hopefully some of that's helpful.